In 2022, the Kingdom of Saudi Arabia unveiled a vision that the engineering world received with a mixture of awe and silent, professional skepticism. A structure called the Mukaab, a hollow cube large enough to contain 20 Empire State Buildings inside its walls. A building designed not merely to be occupied, but to simulate an entirely different sky. As of early 2026, it has not been built. Construction has been suspended pending a sweeping financial and structural viability review. This is the story of why that review was probably inevitable from the start. Let's establish scale first, because without understanding the raw geometry of this project, none of the engineering problems that follow will feel real. The Mukaab measures 400 meters on every axis: height, width, depth. Each face of the cube covers 160,000 square meters of surface area. Multiply that by 6 faces, and the exterior envelope alone approaches 1 million square meters of facade. The interior void, the habitable space inside, covers approximately 2 million square meters of gross floor area across its planned mixed-use levels. The project was designed to house up to 400,000 permanent residents, plus hotels, retail, cultural institutions, and an entertainment district, all inside a single structure. To move materials into and out of this structure on a daily operational basis, the design teams proposed internal transport networks, essentially a transit system embedded within the building itself. Not an escalator, not a lobby elevator bank, a metro. And this is exactly the right moment to pause. If you're fascinated by the engineering that defines our future, hit subscribe and join us here at Next Build. We're tracking these mega projects from blueprint to reality, or in this case, to a complete standstill. Because the gap between those two outcomes is where the most important engineering conversations happen. The first engineering problem is the one that meets your eye. The exterior skin of the Mukaab is designed in the Najd tradition, referencing the geometric ornamentation of Central Arabia's historical architecture. Mud brick patterns, angular repetition, deep shadow reveals. It is aesthetically deliberate, politically significant, and structurally complex. The external skin is not just decorative. It is part of a composite structural system that must handle the dead load of the building, its own mass, plus live loads from occupancy, wind, and in the desert context of Riyadh, seismic activity from the Arabian Plate's interaction with the Zagros fault system to the northeast. The dead load of a structure at this scale is staggering. Even before a single resident enters, the raw structural weight of a 400-meter cube, using conservative estimates for reinforced concrete cores, composite steel megaframes, and the building's internal floor plate systems, places the total structural dead load somewhere between 8 and 12 million metric tons. That is before furniture, before vehicles, before water in pipes. The ground conditions at the Diriyah site present their own challenge. Riyadh's near-surface geology is predominantly limestone, generally competent, but gypsiferous layers exist at varying depths throughout the region. Gypsum is soluble. Under sustained loading from a structure of this mass, differential settlement over decades becomes a primary long-term structural risk. Engineers would need pile systems driven to depths exceeding 60 to 80 meters in places, anchored well into undisturbed bedrock. And then there is wind. The Mukaab's geometry is a square prism, the worst possible aerodynamic profile for a tall structure. A rounded tower sheds wind, a tapered spire redirects it. A cube presents a flat face and catches everything. The Shamal winds of the Arabian Peninsula routinely reach sustained speeds of 60 to 80 kilometers per hour, with gusts recorded above 120. Against a 400-meter face, those loads are not merely structural, they are architectural. The building would flex. And in a structure designed to house hospitals, schools, and an entertainment district inside a single skin, that flex must be controlled to within millimeters. Now we get to the engineering problem that keeps building physicists awake at night: thermal load. Riyadh regularly records peak summer temperatures of 48 to 52 degrees Celsius. In direct sunlight, surface temperatures on exposed materials, glass, steel, even treated stone, can reach 70 degrees or higher. The Mukaab's exterior skin covers approximately 1 million square meters. Each square meter facing south and west during peak hours absorbs somewhere between 800 and 1,000 watts of solar energy. Multiply that across the sun-exposed faces. and you're looking at a solar thermal input that is almost beyond the scale of conventional HVAC engineering. But the thermal problem is not only external. At the conceptual heart of the Mukaab is a proposal that has no precedent in the history of construction. An interior holographic dome, a spherical, immersive digital environment approximately 200 meters in diameter, suspended within the central void of the cube. A screen, a sky, a simulated atmosphere. The power density of the LED and projection systems required to illuminate a dome of that scale, with the resolution necessary to be convincing to residents looking up at an artificial sky, would generate thermal output equivalent to a small power generation facility. Estimates from comparable immersive display projects at much smaller scales suggest the display system alone could contribute 50 to 100 megawatts of waste heat to the interior environment, continuously. To cool this environment, the Mukaab's HVAC system would have to be, by any engineering definition, the largest climate control apparatus ever built inside a single structure. Preliminary design concepts reference a district cooling approach, centralized chiller plants, likely drawing from the grid, pushing chilled water through a distribution network measured in kilometers, not meters. The cooling capacity required to maintain human comfort across 2 million square meters of occupied floor area, plus the waste heat from the holographic dome, plus the solar gain through the outer skin. Conservative engineering estimates place the total cooling load between 150 and 250 megawatts of refrigeration. For context, that is the equivalent of the total electrical output of a medium-sized natural gas power plant, dedicated entirely to air conditioning. One building. Here is where the Mukaab stops being a building problem and becomes a meteorology problem, when you enclose 2 million square meters of habitable space, with residents, vegetation, water features, swimming pools, restaurants, and sports facilities beneath a single climate-controlled roof. You create the conditions for an indoor ecosystem, complete with its own weather. This is not a metaphor. This is atmospheric physics. The interior of the Mukaab, at full occupancy, would generate significant moisture loads from respiration, perspiration, cooking, water features, and irrigation for interior green spaces. The design targets an interior relative humidity of between 45 and 60%, the range considered comfortable for human occupation. But the challenge is the vertical thermal gradient inside the structure. The Mukaab's internal volume is approximately 64 million cubic meters. That is not a typo. 64 million cubic meters of enclosed air. As warm, moisture-laden air rises from the occupied lower floors, it encounters the structurally and mechanically cooled surfaces near the upper envelope. At the interface between warm, humid air and a cool surface, condensation occurs. At scale, across a dome hundreds of meters across, that condensation does not trickle, it rains. The phenomenon is well understood in enclosed agricultural facilities, in large atrium structures, in sports domes. But it is usually managed at relatively small scales, a greenhouse, a stadium, a shopping center atrium. At the Mukaab scale, the condensation management system becomes a building within the building. Engineers would need to integrate condensate collection infrastructure into the upper structural elements, troughs, drainage channels, collection reservoirs, capable of handling precipitation rates that could realistically reach several hundred liters per hour under certain thermal loading conditions. The dew point inside the Mukaab would not be a fixed value. It would be a dynamic variable, shifting with the time of day, the season, the operational state of the holographic dome, and the real-time occupancy of the structure. Managing it requires not just HVAC engineering, it requires what the industry calls building atmospheric modeling. Essentially, weather forecasting for the inside of a building. The Mukaab is not a standalone project. It is the centerpiece of New Murabba, a larger urban development initiative from the New Murabba Development Company, a public investment fund entity. The broader district was conceived as a 40 by 40 square kilometer urban quarter north of Riyadh's existing downtown. The Mukaab itself sits at its center, the anchor, the icon, the proof of concept. Saudi Arabia's public investment fund is simultaneously the funder of the most ambitious portfolio of construction mega projects in human history. The Line, a 170-kilometer linear city in the desert. Neom, a planned technology and tourism zone larger than Belgium. Qiddiya, an entertainment mega-district outside Riyadh, and now the Mukaab. Each of these projects is individually unprecedented. Together, they represent a capital commitment that even the most optimistic projections of Saudi oil revenues struggle to fully absorb on the proposed timelines. In early 2026, when the Mukaab construction suspension was confirmed, sources within the engineering and construction community cited not a single failure point, but an accumulation. The structural loading calculations on the foundation system had grown beyond initial parameters. The HVAC and atmospheric modeling costs had ballooned during detailed design. The holographic dome, the centerpiece of the interior concept, had no vendor in the world capable of delivering it at the specified scale without essentially inventing the technology from scratch. And the overall project cost, by some independent estimates, had grown toward a number closer to $300 to $400 billion. To be clear, the Mukaab has not been cancelled. The official language from New Murabba is a pause for comprehensive review. That is a meaningful distinction in the world of mega-project development. Projects of this scale, the Burj Khalifa, the Palm Jumeirah, the Channel Tunnel, all experienced suspension events during their development. Many survived them, some did not. The Mukaab is one of the most honest buildings in the world, not because of what it would achieve if built, but because of what it reveals about the gap between architectural ambition and engineering reality. Every engineering problem the Mukaab presents has a solution, in theory. Condensation management at 64 million cubic meters of interior volume, solvable. Solar thermal load across 1 million square meters of facade, solvable. 250 megawatts of cooling demand, solvable. A holographic sky dome that has never been built, solvable. But solvable is not the same as affordable. And affordable is not the same as fundable. And fundable is not the same as built. Here at Next Build, we will keep watching, because the history of engineering is full of structures that were impossible, right up until the moment they weren't. And it is equally full of structures that stayed impossible. The Mukaab has not yet declared which story it belongs to. If you want to follow the Mukaab, Neom, and every other mega project that is redefining what cities can be, subscribe to Next Build. We track the engineering from the blueprint to the first shovel and everything in between.